Hey everyone, my name is Ben McDonald. I'm a hardware software engineer working on the hardware management team at HPE, and I'm also an open source contributor to the OpenCHAMI project. So in this video, I'm going to be going over how you can run the OpenCHAMI FRU tracker, how you can use the provided collector in the repo for basic hardware information to store in the FRU tracker, and then how you can modify that collector with Copilot to collect and store the information that's relevant to your specific site. Thank you. So I'll be running through some of the documentation that's available in the Free Tracker repository. And so everything that I'll be going over today is viewable publicly on GitHub, but split up across a couple of files, unfortunately. And so just briefly before I get into this demo, I will mention that this project, this Free Tracker service was generated with Fabrica. And so I won't spend too much time on this, but essentially what Fabrica is a way to build production-ready REST APIs with automatic code generation. So essentially, you get the bulk of your service generated with Fabrica, and then that gives you kind of like standard APIs, Kubernetes-style envelopes, and that sort of thing that you can work with. But then it allows a reconciler, it's called, to make some more unique service-specific code changes that we have in the Fruit Tracker service for reconciling the data that's posted there. And so before I get into this, I'll mention, as kind of is the standard in OpenCHAMI, we have these release projects that have Docker images that you pull and run locally yourself. So that's what I'll be using for this tutorial here, is that public release. And so just to know that process of getting that running here, if we move into the demo repository, here I've kind of got some commands that we can use to actually get this service up and running, just a few simple commands using our Docker. So the first thing we're going to want to do is create this data folder and then give that, all the permissions so we can read and write from that folder from our Docker container. And so I've created that. And then the next thing I'm going to do is pull the Docker image and run the server. And so this command is extremely long and looks intimidating, but all they were just saying is run this Docker container on port 8081, use this Free Tracker latest release that I have pushed up, and then use this data folder that we just created for our SQL backend. And so if I get that run here, what you'll see is we pulled that OpenCHAMI project. I've already pulled it, so didn't do the full pull, but it's your first time, that'll happen. And then we start our server. The main thing that's interesting here is that we're running on port 8081, and we're using a SQLite database. And all these workers are basically just saying, our service is up and running and ready to do things as you change them. And so the next thing in this demo here is to extend the collector. And so with the Fruit Tracker in OpenCHAMI, what we've designed this to be is essentially a hardware agnostic data store for your hardware. So so if we look at the data model that the Fruit Tracker uses, we have these kind of core spec fields that are required for you to store in your object. And that's essentially like a device type where you have nodes, CPU, and DIMM, which are the three things we're collecting as our reference collector implementation. And then other things like manufacturer, part number, serial number, just kind of standard hardware details. But then the interesting thing here is this properties map, which is an arbitrary key value map for additional data. And this is what kind of decouples this requirement of every site has to be the exact same. By using this properties field, you can essentially store whatever you want for your different pieces of hardware to make sure it stays relevant to what is going on at each individual state. And so, like I mentioned, this Fruit Tracker project comes with a collector reference implementation that just collects CPUs, DIMMs, and nodes, like I mentioned here, and just gathers some of the most basic information on that. So, you could just use that, but the idea is everybody's going to want their own information stored, and so they can build upon that. And so I'll just be showing in this demo how you can actually make those changes yourself. And so in order to do that, we're going to be extending our collector. And so here, what I'm looking at is just some output from a DIM on this machine that I've been running on. And so say you're not satisfied with the information we're storing by default, and instead you want to add this capacity megabyte field and something like, see, what was the other one? Oh yeah, this operating speed megahertz. Okay, so those two things are particularly important to you. So then what I've got here is just a couple of prompts that you can pass to GitHub Copilot to actually make these changes in code. And so what we have to actually make these changes in code is this collector plan that essentially just tells GitHub Copilot, like, this is how you actually extend this in a more standard way to kind of keep different code bases consistent. And so if I run this prompt through my GitHub Copilot, it takes a second, as I'm sure you all know who are working with Copilot, but it'll eventually tell me what I need to change to get this working. And I mean, say I don't like to use Copilot, the vector plan is a plan humans could use as well to actually make changes. But figured we would get started with this Copilot here. All right, so we've gotten our new code. We're going to add the capacity megabytes and the operating speed megahertz for each DIM and store those in the properties map. And so what we're going to do here is the first step is we extend our redfish memory struct to store capacity megabytes and operating speed megahertz. And so if we have Copilot those changes, see those go in. And then in collector.go, the reference implementation that I talked about, that just collects some basic fields. If we make these changes here, these ones are a little bit more interesting and ones that are a little more useful for seeing how the benefit of Copilot essentially for making these changes. And so we've got this code here that essentially just adds these new fields to our redfish that we're collecting, our redfish data that we're collecting, and then inserts those into the properties field. And so we've now made those two changes. We've let Copilot make those changes, I should say, and then we can push these up since I'm running on a remote machine. Capacity. I don't know if that is this message, but so we're pushing that to our origins so we can access this on our remote machine. So I'm going to go into this other terminal here, hold down those changes, and then now I've got this collector going to be collecting our DIMMs, CPUs, and nodes, and storing this additional capacity megabytes and operating speed megahertz. And so at this point, all that's left for us to do is run our demo collector against a specific IP address of a BMC that we want to collect the information for. So here, just running that on a IP address that I've already had discovered and know the IP address of our BMC. So you can see it getting started on our collector here, doing some redfish discovery, which takes a second here. And then it posted that data to the inventory, as you can see. And then here you can see in our Fabrica output, we had essentially all these devices getting posted to our service and then linking with their parents. So this is just showing that it works essentially. What is shown there is not particularly important. But so we've got that data stored, and then if we want to take a look at that, we can just query this devices endpoints, which is how OpenCHAMI Fabrica services work. So we're just going to query our service on port 8081 and then the /devices endpoint, which we just created the objects for, and then just piping that through JQ to get some nice JSON output. And so look at that. What we're seeing is now we've got this DIM here, and it's storing all the essential information that I mentioned. And then in this properties field, look at that. We're seeing this new capacity, megabytes, and operating speed, megahertz fields that apply to some standard naming conventions for these objects that are outlined in the repo documentation. And so just to look at a different type of device that we have stored in this repo, here's a CPU, and you can see in the properties field, this has the more basic just redfish URI and redfish parent URI, it doesn't actually contain that new information because we only made that change for DIMMs. And so, yeah, you could do the same thing for CPUs to store whatever information you wanted on CPUs. That was just an example. But yeah, this is essentially how you can run the OpenCHAMI Fruit Tracker service and modify and use the collector locally to um, store whatever information you would like from your machine. And then there are some other information in the fruit tracker that I didn't really go over here, which is the Fabrica, like event bus, discovery snapshots, and seeing how the actual changes can be tracked over time to see changes in hardware over time. But all that information is available in the fruit tracker repository in case there's something more you would like to see, and always open to questions or anything on the repository as well. So that was my demo. Thank you, everybody. See you all at HBSFCon coming up, and thank you.